All right, so in order to save some time, I went ahead and already solved this problem out. And I'm just gonna kind of walk you guys through it now. So basically what's happening is we have this rectangular cross section of a beam that's shown. And I'm gonna scroll up so you can see what we did here in the last video. We were determining stress for biaxial bending, and we wanted to determine the location of the neutral axis in terms of this angle alpha, or in terms of location z sometimes. So for this example here, we want the normal stress sigma developed at each corner of the section, and we want to specify the orientation of that neutral axis, okay? So what I went ahead and did is I calculated the moment in the y direction, the moment in the z direction, and the way that I did that was just by taking the components. So we can see here, this is a 3, 4, 5 triangle. So you just take the components along the z-axis, take it along the y-axis, and you can get the distribution of moment, or the moment value. And then just to note, always use the kind of positive value of the axis that's shown on the diagram. So whenever they put z here, that means this is really positive z. Whenever they put y here, that means it's positive y, and this is positive x. So that means in this picture, if I were to make this into a 2D image, this cross section would look like this, and the y direction being positive would actually go down. This is positive y. Okay, so just follow what the picture kind of gives you. And obviously x would come out of the page. I can't really draw that in a 2D picture. So here for section properties, we have moment of inertia in the y direction. So if I'm taking moment of inertia in the y direction, I'm going to have that 0.4 as my b, and then the 0.2 as my height of the section, because I'm cutting it along the height. That's how you want to think about it, that this would be the axis where you're taking moment of inertia about. So I would be cutting it above and below. And then for IZ, I'd be taking moment of inertia about this axis, so I'd be cutting it above and below, and now that would be my new height. Okay, so this is a good kind of couple of calculations to practice. Make sure you understand that moment of inertia is not just a geometry for any cross section. It's highly dependent on the axis that you're taking the moment of inertia about, and that changes it. And you can always remember this as its resistance to rotation, and rotation is applied about an axis. So that means moment of inertia has to be dependent on the axis that you are calculating it about. Okay, so this is a good kind of reminder to help you remember that, okay? Okay, so bending stress, this is the biaxial bending formula that we derived in the last video. Biaxial bending formula. Okay, and I went ahead and wrote all this out because it was just a lot of writing and a lot less talking, so now I'm going to walk you guys through what I did. So the question asks for the stress, the normal stress at each corner of that cross section. So this would be for each corner, sigma B, sigma C, sigma D, sigma E. And all you'd have to do is go to each corner. So for example here, let's look at sigma B. This is negative mz, so I want to come here, sigma b. What is the negative m moment in the z direction? What's the component moment in the z direction for that? I want to come here, what's mz? 7.2. Literally plug in the 7.2. I'm done with that. The y value here is going to be the distance from the neutral axis to point B. You can see here that's 0.2, plug that in. And then I about the z direction, plug that in. Come to the next part, my, what's the moment contribution in the y? I already calculated that here, times the distance now in the z direction. So if b is here, how far is it from the z-axis? It's 0.1 away, 0.1 away. Plug that value in, and then put in under that my moment of inertia in the y direction that I already calculated, and I just literally get that value, and that's it. Okay, we'll do one more. So sigma C. Sigma at C, where's my C? Here it is, this corner right here. Okay, again, the big changes that you're gonna see here are primarily just with the location that you're measuring from. So here, I measured a positive 0.2, C is also gonna be that 0.2 away, because you're still going up, but now it's going to be that 0.1 away from this direction. Oops, sorry. Okay, so nothing has changed here except in my values of this value right here. I'm now measuring a positive. So you can see here, I was measuring negative 0.1 away. Now I'm measuring a positive 0.1 away because I'm going in the positive z direction. Okay. Here, let's move on. With sigma d, you can see here, I'm going to have the negative 0.2. That would be my y from d. Let me show you here. I would be here, D, and I'd have to measure from the Y direction, this 0.2, and then the 0.1 away, of course, from the Z axis. Okay, so I get all of these values here. And then once I get those values, I'm going to actually do the calculation for the neutral axis orientation with you. This one's a little bit more difficult to kind of grasp and to understand what the picture looks like. So I'm going to try my best to draw in 3D here. Okay. So let me get to this. I'm going to redraw the cross section here. And then of course this is our positive z direction. And this downward direction is our positive y direction. And we know that our moment is being applied in some direction here. Okay, and then we also know that this angle here is our theta. And then we have some alpha that we want to find, right? And we know that alpha is measured from positive z to positive y. That's super important. It's from positive to positive, and so is theta actually. So when we take theta, we want to find theta, we need to take the negative inverse tangent, because I drew theta going above from z to negative y technically, so I'm going to take the negative of it, of 4 over 3, and I get this negative 53.1. This is just given from the geometry. This is a 345 angle that the moment acts about. And so really what I'm saying is it's 306.9 degrees from the 0 mark, because my 0 will be measured downward from this direction. That makes sense. Okay, let me get rid of that so it doesn't confuse anybody. Now to get alpha, I can say tangent alpha is equal to this formula that we calculated earlier, IZ, IY tan theta. Super simple from here. You just plug in the values we already calculated, 1.067 times 10 to the negative 3 divided by 0.2667 times 10 to the negative 3 tangent, and I'm going to keep that negative in because I want to make sure that I know it's calculated from positive z to positive y, and I get negative 79.4, which really just means that I can come up from here and measure 79.4, and this is going to be the location of my neutral axis. Okay, and that's it for this one. So let's move on to composite beams. So basically composite beams are beams that are constructed from 2 or more different types of materials. And some examples of that, we have wood beams that have steel straps to help with load support. And if we remember the flexure formula, it's developed for material that is homogeneous. So we can't really exactly directly use it, but we'd have to kind of modify it if we want to determine normal stresses for composite beams. And there is a way to do that, okay? So what we can do to modify or transform a beam's composite section is we can kind of take whatever the area is of the second material and transform it into an area of the first material, okay? So that might sound really weird and really confusing, but I will show you an example and you'll see how simple that can be. Okay, so consider the following composite beam. What we have here is we have 2 steel plates that have been attached to a wooden beam. And when we apply the moment, the total cross-section is going to remain plane after bending, and then the displacement is continuous, so we have that normal strain that will still vary linearly from 0 to the neutral axis to some maximum located farthest away from the neutral axis. Okay, and here we have all these diagrams basically that shows what happens when we have these 2 different types of materials. Okay, so what we want to do is I'm just going to show you usually here, let me write this down in a space that's empty. We're assuming linear elastic material, right? Linear elastic material. So if we have material 1, let's say we say sigma is equal to E1, some modulus of elasticity times strain. Material 2, we have sigma is equal to some other modulus of elasticity and strain. We're going to assume that E1 is greater than E2, which means that material 1, we're going to pick this, material 1 is stiffer than material 2. Okay, and that's where we get the stress distribution from. Okay, what we're going to do is, so I'm going to actually come back here. These pictures here, these figures show two different types of materials, a stiffer material, that's what this corresponds to, and then a less stiff material. And then you can see what happens is when we transform the sections, now we have, if this was, let's say a wood, let's say this was wood and this was steel, now we have a section that's all wood, but you can see the top part has a larger dimension than the steel plate because we're saying that, hey, if we replace that steel portion with a wood portion, it would have the same stress and strength as it could if we increase the dimensions of it. Okay, and the same thing here. We could transform the wood section to a steel section by just decreasing the dimension. It would have the same stress or equivalent load that it can carry. So that's the idea here. We're not doing this in real life, but we're just doing it so that we can easily calculate what's happening using the flexure formula that we already derived. There's one application that this is super important for, and you might have already realized where we're going with this, but it's for reinforced concrete, which is one of the most common types of beams that include different types of materials in it. So just if we go back to the flexure formula, if we remember, if we have a beam that looks like this, and we apply some transverse load, and that induces some type of bending that looks like this, we have compression in the top, we have tension in the bottom, and we know something about concrete, okay? Concrete is really bad in tension. Concrete performs really poorly in tension. So in order to fix that, in order to help us still be able to build with concrete, what we do is we add reinforcement. We add rebar, steel rebar. Okay, we add rebar to up the tension or the tensile strength of our concrete beams. But when we do that, what happens is you'll see some kind of cross section that looks like this, maybe 2 bars of rebar at that cut. What happens is we now have to transform this section if we want to use our bending formula for it, okay? And we have some pretty simple ways that we can do that, okay? So here, if we're talking about reinforced concrete beams, we have some defined distances that we can use. So we have a distance D, which is the distance from the top of the beam to the steel reinforcement. So I'm going to redraw that picture here for you. This is the cross section. However much reinforcement you have, the distance D would be this. The beam's width here would be this B, and H prime is the unknown distance from the top of the beam to some neutral axis, and that neutral axis location is no longer necessarily in the middle because that reinforcement changes it. So that's what we kind of have to figure out. We have to figure out what H prime will give us that centroid of the cross-sectional area when we transform it. Okay, so we're going to do an example of this here, and hopefully that'll help you figure out how to understand what we do with reinforced concrete beams. So you can see we have a reinforced concrete beam with a cross-sectional area shown, and if it's subject to some bending moment of 60 kips, this is about the z-axis, this is an MZ, right, because this is a bending problem. We want to determine the normal stress in each of the steel reinforcing rods and the max normal stress in the concrete. Okay, so since the beam is concrete, the following analysis will neglect its strength in supporting tensile stress. So we're going to assume that the concrete doesn't really support anything in tension. Okay, so let's start with section properties. We have area of the steel rebar. It's circular, right? Circular cross section, so times pi r squared. We get 1.571 inches squared. And what we're going to do is we're going to transform to an equivalent area of concrete. Okay, so my transformed area is going to be called A prime, and all I have to do is multiply it by some n value times the area of steel, and the n value is a function. It's just the ratio of modulus of elasticity of steel divided by that of concrete that was given. And oops, I forgot to multiply by the area, times this 1.571 inches squared that we just solved for, and we get a new area of that right there. Okay, so this is our steel transformed now to an equivalent area of concrete. And it makes sense because we need a lot more steel now, or sorry, a lot more concrete to replace that strength that the steel is giving to this beam. Okay, so we now have to require the centroid of the beam's cross-section to lie on the neutral axis, right? That was a requirement of our bending formula. We require the centroid of the beam to lie on the neutral axis. If that's the case, we would need to satisfy this formula. So we would say that 12 inches times some h value, the location of my neutral axis, h prime, sorry, and times h prime over 2 minus this equivalent area of steel and turned into concrete times 16 inches minus h prime has to be 0. So the center of each of those, this would be the center of each of those areas times the area of those areas, right? This is the centroid of steel plus centroid of concrete. And this picture shows you everything that we just calculated here. And we get this function here, h prime squared plus 2.11 h prime minus 33.7 equals 0. And this is a second order function. We can solve for this and take the positive root. So solve for positive root, and we get h prime is 4.85 inches. And we'll use this for the moment of inertia calculation for our transformed area. So here, now our moment of inertia, we have 1/12 times 12 times 4.85 cubed plus 12 times 4. This is parallel axis theorem. And then plus our steel section times the 16 minus 4.85 squared. And we get a total value here of 2,029 inches to the fourth. And now we can find our normal stress by applying the flexure formula. So I'm going to come here, normal stress. And we can apply the flexure formula to our transform section and say sigma of concrete max is equal to that 60 kip-foot. This is the applied moment that was given in the problem. I'm going to convert it here to inches times the 4.85 inches. This is the C value. This is the location of the neutral axis, remember, that we just calculated, times divided by moment of inertia, and I get 1.72 KSI. And then here, I want the normal stress that's resisted by concrete strip, which replaced the steel, right? So I want the normal stress that is resisted by the concrete that replaced the steel rebar. And I can calculate that as sigma prime of the concrete is that 60 times 12 inch per foot. This is feet times now the distance from the neutral axis divided by that 2029, and I get 3.96 KSI. And then I want the normal stress in each of the two reinforcing rods. And I get sigma steel equals N sigma prime of concrete. So I can say 29. I'm converting this back now to the steel. And this is my answer along with this. Okay, and this graph shows the normal stress right here. This is a graphical picture. So we have the 1.72, which is the normal stress of the concrete, and the 31.9, which is the normal stress of each of the steel rebar that we added. Okay, so this concludes topic 5, which is all about bending, and the next video is going to be topic 6, which is transverse shear.